This time we're going to look at another linear programming example, but we're going to move a little bit more quickly. Let me turn on my graph paper here. There will be some graphing involved because we're optimizing an objective function within constraints, so we have to find a feasible region. So let's start with the problem. I'm going to type it up. If you're taking notes, you may want to handwrite it. So we say a company manufactures two sizes of gears. The small gear requires 4 hours of machining and 1 hour of polishing. Each small gear yields a profit of $35. The large gear requires 1 hour of machining and 1 hour of polishing. Each large gear yields a profit of $20. The company is limited to 24 hours each day for machining. That makes sense. And 9 hours each day for polishing. How many of each type of gear should be made each day to maximize profit? And furthermore, what is the maximum profit? Okay, so a lot of stuff going on here. So we have to start dissecting this paragraph. And the first thing we look for is we need to identify our two variables x and y. And so since the problem says how many of each type of gear, let's let x represent the number of small gears. And really that's how many small gears manufactured each day. But this is sufficient. Let x represent the number of small gears. Let y represent number of large gears. So we're trying to figure out what x and y are to maximize the profit. Okay. The next thing we need to figure out is the objective function. The objective function is what we're trying to maximize. So in this case we want to maximize profit. So the objective function is going to be a profit function. So P equals, and we have to find a formula to calculate profit. So we want to maximize profit. That's going to give us our objective function. So we start searching through here, and we need to figure out how much profit each gear gives us. So small gear yields a profit of $35. Well, if we make X gears, then 35 times X is how much profit we'll get from the small gears. And large gear the large gear yields a profit of $20. And if we manufacture Y, large gears, then 20 times Y is how much profit we'll make on the large gears. And if we add those together, that's our total profit for both gears. Okay? So that's our objective function. The next part's typically the hardest part, which is identifying the constraints. So let's, first of all, so if we look at the constraints, since x and y represent the number of gears, we know that you can't make negative gears. So x and y are both greater than or equal to 0. So those are implied constraints that aren't explicitly stated within the body of the problem. So that's kind of hard to remember sometimes. So always think about if you can have negative values for your x and y. If not, then you need to require these constraints. Okay, so let's go through and highlight our limitations. So small gear requires 4 hours of machining, 1 hour of polishing. There's no limitations there, that's just a fact. Large gear requires 1 hour machining, 1 hour polishing, no limitations. Alright, the company is limited to 24 hours each day for machining. So we need to come up with a way to describe that. We have to spend less than or equal to 24 hours a day on machining. Well, how many hours is required for each small gear? So for each small gear, gear requires 4 hours of machining, and each large gear requires 1 hour of machining. So the total hours of machining, well, if we have X small gears and each of them requires 4 hours, then that's 4 times X total hours of machining for the small gears. Similarly, 1 times Y, or just Y, since Y is the number of large gears, is the number of hours machining large gears. If we add those together, that's our total hours of machining, which has to be less than or equal to 24. So that's our machining hours. Okay. All right. Last, the company is limited to 9 hours each day for polishing. So that means we have to be less than or equal to 9 total hours for polishing. And we have X gears, each one of those requires 1 hour of polishing. So that's 1 times X hours, which is just X. And each large gear requires also 1 hour of polishing, so that's 1 times Y, or just Y hours. If we add those together, we have to be less than or equal to 9. And those are the constraints. We have no other limitations in this problem. So now, that's the hardest part right there, in my opinion. So now what we have to do is find the feasible region for the constraints. We have to graph all of this. Once we get our feasible region, we need to identify the vertices and plug them in to our profit function to see what gives us the maximum profit. So here we go. Let's set up our plane. Now, because I know X and Y are both greater than or equal to 0, when I graph this, I know I'm limited to the first quadrant. So that's going to help me set this up. And let's go ahead and set up, we need to set up a scale. So it's going to be useful here. Actually, let me do this. Let's get rid of that. It's going to be useful to identify how to graph each of these two inequalities. These top two are simple, but the last two are in standard form. So to graph those, it might be useful to find the intercepts. So the first inequality, if you think about if it were an equation, if it were a boundary line, it'd be an equation. If X is 0, then we get Y equals 24. And if Y is 0, then we have 4X equals 24. And if you divide by 4, that means X is 6. And if you test, so we got 2 points, that's enough to see the boundary line, but we have to know which side to shade. If you test the ordered pair 0, 0, 0 plus 0 is less than or equal to 24. So that means we need to shade the 0, 0 side of this line. Okay? Alright, the next one, same process. So plug in 0 for X, which means Y equals 9. Plug in 0 for Y, which means X equals 9. Plug in 0, 0. Well, 0 plus 0 is less than or equal to 9, so we will again shade the 0, 0 side. So make sure you do that test point. Don't always assume that you'll shade the 0, 0 side. Okay, so now we have enough information to put together a graph. So it looks like we need to go from 0 all the way up to 24. So let's go, let's see. Let's go in intervals of, hopefully 2 will work. Let's see. So this will be 2, 4, 6, 8. There's 10. The x values never get bigger than 9, so we'll leave, that's big enough on the x-axis. The y-axis is where we need to go up to 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay? Alright, let's start graphing our constraints. So let's graph x is greater than or equal to 0. Well, the boundary line here is the y-axis. The boundary line is the y-axis, x equals 0, and since it's greater than or equal, we need to shade to the right. Okay, so we're talking about everything to the right of the y-axis. If we look at y as greater than or equal to 0, the boundary line is the line y equals 0, and because it's greater than, we need to shade above. So at this point, we're to the right of the y-axis and above the x-axis, so we're talking about the entire quadrant would be shaded if those were our only two constraints. Let's graph the next two. So the next line goes through the point 0, 24, which is up here, and the point 6, 0. So we'll graph that line. Looks something like this. Let's label that boundary line equation. 4x plus y equals 24, and we need to shade the 0, 0 side. So now, rather than the entire quadrant, we have to limit ourselves to the 0, 0 side of this line. So we're looking at this triangle. Okay, the next one, we need to go through 0, 9. That's right there between 8 and 10. And 9, 0 is also between 8 and 10. So our boundary line this time looks like this. The equation is x plus y equals 9, and we need to shade the 0, 0 side. So now, rather than the triangle, we have to cut it off and be on the 0, 0 side of that line and the 0, 0 side of that line. So our feasible region is this quadrilateral, this four-sided polygon, which happens to have 4 vertices, okay, 4 corners. So 3 of them are simple. The ones on the axes are simple. The top one, let's do this. We'll write them underneath. So the vertices are 0, 9. The bottom left corner is 0, 0. The bottom right corner is 6, 0. And we need to figure out this guy. So this guy is where the 4x plus y equals 24 line intersects the x plus y equals 9 line. So I need to find the intersection of these two lines by solving this system for x and y. So what I'll do is I'll use elimination here, so I'll multiply the second equation on both sides by a negative. So now I have 4x plus y equals 24, and negative x minus y equals negative 9. When I add those together, I get 3x plus 0 equals 15. And if I divide by 3, I can see that x equals 5. Then I need to plug 5 back into one of these equations. So I'll plug it into x plus y equals 9. So 5 plus y equals 9 means that y equals 4. So our last vertex is 5, 4. And that seems reasonable. This looks like it's about 5, and this looks like it's about 4. Okay? Alright, so we have our 4 vertices precisely labeled now. We need to take those and plug them into our objective function, p equals 35x plus 20y. So p equals 35 times x, oh I forgot already, plus 20y. So in this case, 0 for x, 9 for y, so 35 times 0 plus 20 times 0, 35 times 6 plus 20 times 0, and last we've got 35 times 5 plus 20 times 4. So now we just need to calculate our profit for each of these. So 0 times 35 is 0, 20 times 9 is 180. So that means, remember what x and y represent, right? These ordered pairs are x and y. X is the number of small gears, y is the number of large gears. So if they manufacture 0 small gears and 9 large gears, the profit will be $180. If we manufacture 0 of each, the profit will be 0. If we manufacture 6 small and 0 large, let's see, that's $210. So our profit, so far, this is our highest profit. The last one, let's see here, 35 times 5 is 175, plus 80 is 255. So that means that's our highest profit. So manufacture, let's answer the question now. We need to figure out how many of each gear needs to be made, and how much profit will it give. So manufacture 5 small gears and 4 large gears for a max profit of $255 per day. And that's a quick run through of all the pieces of a linear programming problem, where we're trying to, in this case, maximize profit based on manufacturing constraints.